Hello everyone. This lecture is going to be on chapter 1.6, which is the transformations of functions. What that means is by looking at the equation of a function, we can tell how the graph of that equation is going to look compared to the graph of the basic function. All right, so once we go into it, once we go deeper into it, it'll make sense what transformations is. But for now, just go along. Now these are the topics we are going to cover. First, we are going to recognize the graphs of some common functions. There are some basic functions like f of x equals x squared, or f of x equals the absolute value of x, or f of x equals x, and so on. So we are going to look at some common functions, linear functions, quadratic functions, cubic functions, etc., absolute value functions. And then we are also going to be able to know from the equation of the common functions what their graphs are going to look like, what the basic graph is going to be. And then we are going to see what would cause those graphs to slide up or down. Vertical shift means up or down, correct? So we should be able to figure out by looking at the equation whether the graph is going to slide up the y-axis or down the y-axis. Likewise, we should also be able to recognize when a graph would slide to the left or right along the x-axis, which means horizontal shifts. Horizontal means left or right, correct? So we should be able to recognize by looking at the equation whether the graph is going to slide left or right along the x-axis. Then we'll talk about reflections to graph functions. And reflection means a mirror image, kind of. All right, so we'll go into that. And then vertical stretching and shrinking to graph functions. So by looking at the equation, we should be able to tell whether the graph is going to stretch or whether it's going to shrink. It's going to narrow down or it's going to be a wide graph. And then use horizontal stretching and shrinking. So there's going to be vertical stretching and shrinking, and there's going to be horizontal stretching and shrinking. Just as there's going to be vertical shift and horizontal shifts, we are going to study what's the difference between shifts and stretching and shrinking. And then we are going to combine all of these in an equation and be able to determine how the graph is going to be when we combine the different sequence of transformations. All right. Now here are some common functions. We said we would look at some common functions to begin with, and here are some common functions which we should be familiar with. F of x equals c, where c is a constant value. So you may have worked with equations that look like, or functions that look like, f of x equals, I don't know, 8. All right, where on the other side, it's not an equation, but it is a constant value. All right, so that's what the constant function is. Constant function. Then we have f of x equals x, which is the equation of a line. It's a linear function. Then we have f of x equals the absolute value of x. All right, and the graph of this is a V-shaped graph. F of x equals x squared is a quadratic function. All right, a quadratic function is one where the highest degree in the equation is a 2. It's a square. So this is a quadratic function. Then we have f of x equals square root over x. We have f of x equals x cubed, and then we have f of x equals the cube root of x. Now it is essential to know the characteristics of the graphs of these functions. All right. Uh, so in the next few slides, we are going to go through the graphs of each of these functions, how they look like. So we should be able to immediately, when we look at the functions, we should be able to picture in our mind what the corresponding graph, the shape of the graph is going to be. For example, and we'll go into more details in subsequent slides, but the graph of a constant function is going to be a horizontal line. Okay, it's going to be a horizontal line. The graph of a linear function where it's f of x equals x is going to be a slanted line with this passing through the x-axis. Then the graph of the absolute value of x is going to be a V-shaped graph. It's going to be a V-shaped graph, whereas the graph of x squared, f of x equals x squared, is going to be a U-shaped graph, turned up or turned down. Likewise, the graph of the absolute value of x can be a downturn V also. The graph of f of x equals x can be a line sloping down from left to right, and so on. And we'll discuss the other ones too in the later slide. So let's just go on and look at the next slide, which talks about the graphs of a constant function. So graph of a constant function is of the form f of x equals c. The domain of this function is negative infinity and positive infinity. Again, what is domain? Domain refers to all the x values that can be plugged into a function, that can be input into a function. And in a constant function, x can take any value. X can take any value from negative infinity to positive infinity. However, the y value is going to be whatever value c is. If it's f of x equals 8, the y value is going to be 8. So that's why it says the range of this function is c, whatever value c is. Again, range represents all your y values. So no matter what the x values, what x value we input into this function, the y value is going to be whatever c is, 8 or negative 5 or whatever, doesn't matter. Whatever c is, that's the only value y will take. The function is constant on negative infinity, comma, infinity. So that means it's going to be the same value no matter what x values we choose. That's what this statement means. The function is constant on negative infinity, comma, infinity, and this function is even. Even function means that if we plug in, and I think we did that in a previous section of chapter 1, what is an even function? If we substitute in f of x, if we substitute x with negative x, we will get back, the function will be unchanged, f of x. All right, so if we evaluate the function using negative x for x, we will get back the original function, which is f of x. It will not make any change, it will not make any difference to the original function. All right, so that's what an even function means, and the constant function is always an even function. All right, so these are the properties of the basic properties of a constant function. Now let's look at the function of f of x equals x. All right, it is a linear function. The previous function, which was a constant function, is also a linear function, but it was a line which would always be a horizontal line, okay, crossing the y-axis at C. Here, this is f of x equals x. It is also the equation of a line, but it's called the identity function because whatever value we input into x is going to be the y value. Okay, it's going to be, y value is going to be identical to the input value of x. All right, so if x is -1, f of x is going to be -1. If x is 0, y value is going to be a 0. So that's why it's called an identity function. It's the graph is a slanted line crossing the um, x and y axis at the point of intersection, which is 0, 0. The domain, the x values that can be input into the function, here we can plug in any value of x from -infinity to +infinity. So we write the domain of this function is -infinity, infinity, and then surround them by brackets here. The range, that means the possible y values, are also -infinity, infinity, because if it's an identity function, y value will be whatever the x input value was. The function is increasing on -infinity, infinity. So all the way from -infinity to +infinity, the graph is rising from left to right. As we move from -infinity to +infinity along the x-axis, the y values are increasing. All right, the y values are increasing, and that's why it's called an increasing function, and the function is odd. That means that um, if we substitute, what does odd function mean? Just to uh, review that here. If we replace x by negative x, if we replace x by negative x, then the y value will be negative. So it will be negative f of x. All right. And if we see that if we replace, um, if we input a negative value into x, then the y value will also be negative. It will be negative f of x. That's what makes it an odd function. And the function, the identity function, is indeed an odd function. All right. The absolute value function is f of x equals the absolute value of x, right? These vertical lines imply that this is an absolute value. All right, that means whatever comes out of this function is f of x is always going to be a positive value, right? Absolute value functions always produce a positive value. Now the domain of this function is -infinity, infinity. So you can input any x value starting from -infinity all the way to +infinity. Your y value is always going to be positive. All right. So if you choose -2 for your x value, the absolute value of -2 is going to be a positive 2y value. All right. So keep that in mind in case you've forgotten. An absolute value always an absolute value function always produces a positive value for an answer, for the y value. All right. The range therefore is going to be anything from 0 to +infinity. All right, y values are always going to be positive. It should not be negative infinity comma infinity. It's going to be 0. It's the lowest value that the y is going to take, and it can be all positive values up to infinity. The function is decreasing on x equals negative infinity to 0 and increasing on x equals 0 to positive infinity. So what does that mean? That means we see, look at the graph here. It's a V-shaped graph, and the V meets at the point of intersection of the x and y axis, 0 comma 0. And we see that as we move along the x-axis from the left hand to the right hand side, that means as the x values increase from negative infinity and goes towards 0, the graph is falling. Okay, the graph is falling, and then at 0 it makes a turn and starts increasing. All right, so that's why it says the function is decreasing on x equals negative infinity to 0. It's decreasing, it's falling, and then it increases from 0 onwards. It increases and keeps increasing all the way to positive infinity, and this function is even. All right, so if we replace x by negative x, then we will still get the same value, positive value for y. All right, we will get back the original function. Another common function is the quadratic function, which is f of x equals x squared. That's the base function. That's the basic quadratic function. And then we will talk about later on of transformations of this basic quadratic functions and any other functions. That's what transformations are about. But we should understand what the properties of the quadratic function is. The shape of the quadratic function is a U-shaped graph turned up. That's the graph of the basic function, which is f of x equals x squared. The domain, that means what are the x values you can input into this function, any value of x from negative infinity to positive infinity. What are the y values that can be produced from this function? 0 comma infinity. Like the absolute value function, the basic quadratic function will always give positive y values. Why? Because whenever you square a negative value, you end up with a positive value, correct? The negative 2 squared is always going to be positive 4. Negative 7 squared is going to be 49, correct? So whatever value, whatever negative value you square, whenever you square a negative value, you should always come up with a positive value. And that's why it says here the range of the quadratic function can be 0 and any positive number all the way to as high as you can reach up to infinity. And please note that here we have a square brackets, meaning that 0 is included in the set of y values that can be generated from the standard quadratic function. The function is decreasing on the x values from negative infinity to 0. So here too, just like the V-shaped graph before, we see that the U-shaped graph also keeps dropping, keeps falling as we move from negative infinity along the x-axis to 0, and then after 0 it makes a U-turn and keeps rising, correct? So this means that the function is decreasing on minus infinity comma 0, and these refer to the interval along the x-axis, and it increases as we move from 0 towards infinity along the x-axis. All right, it will keep increasing as we move from left to right along the x-axis. And the function is even. That means if we replace the x value with its negative version, we will get back a positive value. So in other words, f of 2 is positive 4. F of negative 2 is also positive 4, right? That's what an even function means. That if you replace the x value by its negative version, you will still get the function, the y value is unchanged. You will get the same y value. That's what makes it an even function. The next common function is that of a square root function. So f of x equals square root of x. So here's how the graph looks like of the square root function. So let's look at some of the characteristics of this function. The domain of this function is 0, infinity. All right. So the values that we can input into this function. Okay, let me just remind you this, that in a square root, we cannot have a negative value. We cannot have a negative value. So negative square root of negative 2 does not exist. It will produce an imaginary number. All right, square root of negative 4. Square root of 4 is fine. Square root of negative 4 does not exist. It's not a real value. It's an imaginary value. So you cannot have a negative value under a square root. You can have a negative value under a cube root. Negative 8. A cube root of negative 8 is negative 2. This is real. This is a real number. But the square root of a negative value does not exist. It exists in an imaginary form. It's not a real number. Therefore, we always have to make sure that we don't end up with a negative value under a squared radical. All right. So the domain of this function is 0, infinity. So square root of 0 is good. Square root of 0 is 0. That's fine. All right. Square root of 1 is 1. Square root of 2 is not an integer value, but it is a real number. All right. So the domain can take all values starting from 0 and including 0. It can be 0, and that's why it has the square brackets. It has the square brackets on to its left of 0. That means 0 is included in the set, and any positive number all the way to infinity. The range of this function is always 0. All right, starts with 0, same as the domain, starts with 0 and can be any value all the way to infinity, depending on what the x value or how high the x value is. Then we see the function is increasing in the interval 0, infinity. So that means as we move from 0, okay, this side doesn't exist in the domain. Okay, the negative values don't exist in the domain of the square root function. We can only start from 0, and as we proceed from 0 along the x-axis, the y values increase, right? So it is an increased function. At some point you see it slows down. It doesn't rise the same way as it does in the earlier stages of the function, but they do keep increasing. All right, so the function is increasing on the interval 0, infinity along the x-axis, and the function is neither even nor odd. Okay, the function is so here we have a cubic function, and the form of the function is f of x equals x cubed. It's got the standard cubic function. So let's look at the graph of the standard cubic function. This is how it looks like. It has negative values for y, so you see the graph extending along the negative y values and negative x values and negative y values, third quadrant. The domain of this function, that means the input, the x values that can be input into the function, any value starting from negative infinity to positive infinity, we can plug in any value for x. The range values, the y values that will be output from this function, again, can be any value from negative infinity to positive infinity. The function is increasing all through, so as we move along the x-axis from the negative side towards the positive side, we see that the y values are getting larger and larger. It does slow down at some point towards the center, and then again it rises steeply up here, right, on as x increases. And this function is odd. What does, again, odd function, what does that mean? It means if we replace our x, all right, if we replace the x with its negative version, that means if we replace x with negative x, we will end up with a y value which is the negative of f of x. That means the negative of whatever value we got when we plugged in a positive value for x. So let's quickly run an example. Let's say we have f of 2. Here 2 is a positive value, so 2 cube, f of 2 equals 2 cube, which is 8, correct? If we replace the 2 with a negative 2 for x, all right, we replace this 2 with negative 2, what do we get? Negative 2, again, surround the negative 2 into with brackets, surround it with brackets, and then cube it. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8, correct? So we got the negative of whatever we had when we plugged in a positive 2. So that that's what is meant when we say that when we replace positive x by its negative version, then we end up with a y value which is negative f of x. All right. And finally, we have the uh, cube root function, which is f of x equals cube root of any x value. So this is how the graph looks like. Right, the domain of this function is negative infinity comma infinity. So keep in mind, for the square root function, that we cannot input negative values into a square root function. All right, however, for a cube root function, the cube root of a negative value is it produces a real number for a y value. It's not an imaginary number. So negative values are allowed to be input into a cube root function. So the domain can be any value from negative infinity to positive infinity. Likewise, the range of this function is also negative infinity comma infinity. The function is increasing throughout, right? As we move from negative infinity to positive infinity, the function keeps increasing, so it is a constantly increasing function. and the function is odd. That means f of x, if x is replaced by a negative x, then it will produce a negative f of x. In other words, we have f of x, all right? So cube root of 8 is positive 2, all right? If we replace x by its negative version, so let's replace the positive 8 by negative 8 and find its cube root, we will get a negative 2 for the y value. So in other words, when we replace x by negative x, it gives us negative f of x. That's what makes an odd function. When you replace the x value by its negative version, then you will get negative of the y value that you got from f of x. All right, so it becomes negative 2. What was positive 2 for the y value for f of x becomes negative 2 when we replaced 8 by negative 8. Okay, so that's what makes it an odd function. Now that we have talked about the graphs and properties of the common functions, of a few different common functions, we will go into the transformations of those functions, which this chapter is about. So we'll talk about transformations. Now there are different types of transformations. Transformation is the umbrella word that encompasses all different types of transformations, like vertical shifting, moving up or down the vertical y-axis. It could be horizontal shifting, that means the graph would slide to the left or to the right from its original position, or it could be stretching, it could be shrinking, it could be reflections. So all those would be considered as transformations of a graph from its original function. All right, so we'll start with vertical shifts. Now vertical shifts are um, of of this um, of this format. Okay, vertical shifts are indicated by a plus k. K is any variable, all right? So if you take a function, if you take the original function and add add a certain value denoted by the variable k, any value, then it would indicate, depending on whether k is positive or k is negative, the graph will slide up or down along the y-axis. All right, so I'm just going to go ahead and read the verbiage on this slide. It says, let f be a function, all right, and k a positive real number. F can be any function. It can be a quadratic function, it can be an absolute value function, it can be a cubic function, it can be a square root function, it can be any function, and k any real number. All right, so the graph of y equals f of x plus k is the graph of y equals f of x shifted k units vertically upward. And if k is a negative value, then the graph slides vertically down. All right, so very quickly, let me just try to show graphically what this means. So let's say we have a function f of x equals x squared. All right, x squared, as we know, is a u-shaped, it has a u-shaped graph with its vertex anchored at 0, 0. That's the graph of the original x squared function, okay, the basic quadratic function. Now if we transform this quadratic function and write it as f of x equals x squared plus 2, all right, x squared plus 2. What this means is k has a positive value, all right? So the original form is f of x plus k, all right? So we have to look at the value of k. If k is a positive value, if k is positive, then the graph slides up k units. The graph moves up the vertical axis. If k is negative, is a negative value, then it slides down 2 units along the y-axis. So the graph of f of x equals x squared is going to have its vertex at 0, 0. Okay, 0, 0. But if we transform the original equation and write it as x squared plus 2, then the graph is going to slide up 2 units along the y-axis. So using a different color, okay, it's going to move up 2 units. Everything else is going to stay the same, except that the graph has now the vertex has changed position from 0, 0 to 0, 2 to 0, positive 2. If the function were to be written as x squared minus 2, x squared minus 2, I'm going to rewrite x squared minus 2 in this form here, f of x plus k. So what happens, it's going to be, I'm trying to locate my cursor. Okay, I'm going to rewrite x squared minus 2 in the form f of x plus k. So there's going to be a plus, all right? So the form has a plus in it. So I'm going to write it as x squared plus minus 2. And that value is the value of k. All right, that value is the value of k. That means it slides down 2 units along the y-axis. So if this is -1, this is -2, it slides down. Oops. The vertex is now located at 0, -2. Is 0, -2. Okay, and another thing to watch is that in vertical shifts, you first calculate your y value, all right, and then to every y value you add a quantity, add or subtract a quantity. All right, so, and we'll do an exercise on that and it'll make more sense at that time. The next slide is an example of vertical shift. They use a different function. I've showed you with the quadratic function, the x squared function. They will, in the next slide, we will go through an example which uses the absolute. Okay, so here is the example I was talking about. It says, use the graph of f of x equals absolute value of x to obtain the graph of g of x equals absolute value of x plus 3. So what do we do here? This is of the form f of x plus 3, isn't it? Here, it's of the, remember the form of the vertical shift is y equals f of x plus k. That's the form. So here we see the original function is absolute value of x. We know that it has a graph which is a V-shaped graph, a V-shaped graph which has its vertex at 0, 0. That's the graph of the absolute value, the basic absolute value function. So we've transformed this to absolute value of x plus 3. So again, the form being f of x plus k. So the function is absolute value of x plus 3, correct? So what is the value of k here? K is 3, all right? K is 3, which means the graph, the graph of absolute value of x plus 3 is going to move up 3 units from the original function's graph. All right, so let's look at what they've done here. The original graph was this blue graph, the graph of f of x equals absolute value of x anchored at 0, comma 0. We were expecting that the graph of g of x should move up 3 units. Did it? Yes. The red graph is the transformed graph. So it's moved up 1, 2, 3 units. Everything else remains the same. The shape, the direction, everything else remains the same. It has just moved up. It has just climbed up the y-axis by k units, whatever the k is. In this example, k was a positive 3, so it moved up. If they gave us a function, if the transformed function, let's say it's h of x equals absolute value of x minus 3, all right, that means it's k is 3 because the original function is f of x plus k. So if we rewrite this in the generic form, f of x is absolute value of x, then a plus, then the k is minus 3. K is minus 3, correct? So the minus is a value of k, all right? So when k is negative, that means you are moving down 3 units, 1, 2, and 3 units, right? So everything else remains the same. You are just moving down 3 units if k is negative. All right. Okay, now we will go into horizontal shifts. Now look at the form of the horizontal shift. It's y equals f of x minus f of x minus h. So first of all, I want to point out the difference in the form of horizontal shifts and vertical shifts. So I'll just take a quick minute to remind you what the vertical shift form was. So for vertical shifts, it was y equals f of x plus k. All right, that's what the form was. So what that implied was that we first evaluated y, and then to every y value we added a quantity plus k, or if this was a minus, if k is minus, then we subtracted a quantity from the y value that was already calculated from the original function. All right. In horizontal shifts, look at the form. It says first you add or subtract a quantity to x, and then you evaluate the y value. All right. So first we are adding a quantity or subtracting a quantity, as the case may be, to x, and then we are evaluating the function and finding the value of y. Whereas in vertical shifts, we first evaluate our y value and then add a quantity to the y value. All right. In the case of horizontal shifts, we first add or subtract x by a certain quantity and then we evaluate the y value. I hope you see the difference between the vertical and horizontal shift forms. So what this says is let f be a function and h a positive real number. So h is the variable h is used to indicate the horizontal shift. What does horizontal shift mean? It means that the graph will be sliding either to the left or to the right depending on the value of h. Okay, so let f be a function and h a positive real number. All right, now h is if h is a positive value, all right, if h is a positive value, then the graph is going to slide to the right. So let me write that down here. Okay, if h, so if h is positive, graph slides to the right. If h is negative, graph slides h units to the left. So here we are talking about the h. All right. So I'm going to go and here's an example on the horizontal shift. It says here, use the graph of f of x equals square root over x. So this is a square root function to obtain the graph of g of x equals square root over x minus 4. So as we can see, we should be able to immediately recognize that this is going to represent a horizontal shift because we are first subtracting a value, a quantity from x, and then we are taking the square root, and then we are evaluating the function to come up with a y value, All right, so this will represent a horizontal shift. Now, the form is, okay, the form of the horizontal shift is f of x minus h. All right, and we said if h is just this h, we just have to look at the h. All right, not this minus, not, okay, keep that out of the value of h for the time being. So if h is a positive value, then it shifts right. Okay, it shifts right, positive, then right. If h is a negative value, then it shifts left, then left, moves left along the x-axis. So by how, this is negative, right? So let's put this in this form, f of x minus h. So we have square root, right? I'm going to write that again here to keep it clean. It says g of x. So let's do that. G of x equals square root over x minus 4. Okay, but our form was f of x. Okay, the form was what? X, f of x minus h. All right, so this x, okay, we have this x corresponds to the x uh, in the generic form, and then we have a negative, okay, and then we have a negative, the minus sign that corresponds to this minus sign, and then what is h? This part is h, right? H represents this part. So h is positive 4. Okay, h is positive 4. You have to exclude the minus because the original form or of the transformation of the horizontal transformation is x minus h. So we have to fit the given equation, the given function in exactly this form. So this x corresponds to this x corresponds to this minus corresponds to this minus. So what is remaining? The 4. And this 4 represents our h, which is a positive 4. All right, so that means it is going to, because h is positive, the graph is going to shift 4 units to the right. So the graph of square root over x was started from 0, 0. So the graph of square root over x minus 4 is going to shift 1, 2, 3, 4 units to the right. All right, why? Because h, once we put our graph, our function, rewrote our function in the form of horizontal transformation, we found h was a positive value and the graph shifted 4 units to the right. All right. We completed the vertical and horizontal shifting in the past few slides. Now we are going to talk about reflections, which is also a form of transformation of graphs. All right. So there are two types of reflection. Reflection means mirror image, right? You see your reflection on the mirror, uh, and the same thing applies for functions and graphs as well. Only thing is that the reflection, the mirror here, is either the x-axis or the y-axis. All right, so x-axis, it says here, reflection about the x-axis. So if I draw my x-axis, which is a horizontal line, then the reflection of a graph, which, let's say this is a graph, okay, this is a graph of f of x. When we say it is reflected about the x-axis, that means it's going to look like this. It's going to appear on the other side of the x-axis. All right, and the graph, the reflected graph, will be of the form minus f of x. That means you all the y values found from f of x, all the y values found from f of x will be negated when a graph is reflected across the x-axis. So think of the mirror as your x-axis when we talk about reflection about the x-axis, and the original graph gets reflected across the x-axis, so it appears on the other side of the x-axis, and that happens when all the y values get negated. All right, so all the y values are negative y values. Reflection about the y-axis. In this case, the mirror is our y-axis, which is the vertical axis, correct? It's the vertical axis. So if we have a graph, all right, let me think what would be a good graph to use. So if we have a graph which goes like this, all right, let's say this is the graph of f of x. When it is reflected about the y-axis, it's going to look like this. It's going to appear on the other side, trying to get a different color here to keep the reflected graph different. I'll use the purple maybe. Okay, this is reflection about the y-axis, And what happens, you see here, the graph of y equals f of negative x. So it's now f of negative x. Okay, so when a graph is reflected across the y-axis, across the vertical y-axis, that means what has happened is all the x values, okay, all the x values were first made negative and then the y values were evaluated. All right, just like there's a difference between the form of the vertical shifting and horizontal shifting, we have f of x plus k when f of x is first evaluated and then you add a quantity to it or subtract a quantity from it. For the horizontal shift, if you remember, we first add a quantity or subtract a quantity from x and then evaluate the function to get our y values. In this case, when we reflect about the x-axis, then the y values were first evaluated and then negated. Then it implies a reflection about the x-axis. Y values were first evaluated and then negated. Whereas with reflection about the y-axis, we first negate, we make the x values negative and then evaluate the function to get a y value. I hope you understand the difference. All right. Let's go through an example of reflection about the y-axis. The question is, use the graph of f of x equals cube root of x to obtain the graph of h of x equals cube root of negative x. So the base graph is the cube root function, all right, cube root of x, and they want us to sketch the graph of cube root of negative x. So note here what they've done is in the transformed function they have replaced the x with negative x and then we find the cube root to get the y value. All right, the base function, the base cube function has this blue graph. All right, it has this blue graph. Now, when we replace the x with a negative x and then evaluate the cube root of it, we take the cube root of it, it is a reflection about the y-axis. So think about it as the y-axis being the mirror. So everything gets reflected across the y-axis. Now, if we look at this part by part in two parts, I think it'll be easier for us to understand. So reflection along the across the y-axis means what appears the top part of the graph, all right, the top part of the graph is reflected across the y-axis. So the reflection of this blue graph is this red graph across the positive y-axis, whereas the reflection of the lower part of the graph, this blue part of the graph is reflected across the negative y-axis. So this part, this red portion of the graph is the reflection of the lower part. So together, all right, this whole red graph is the reflection of the cube root function when we replace x with negative x and then find the cube root. So whenever that happens, whenever x is replaced by negative x in any function, cube root function or square root function or squared quadratic function or absolute value function, whenever the x value is replaced with its negative version and then we evaluate the function to find the y value, it's always a reflection about the y-axis. So far, the transformations that we have talked about are vertical shifting, horizontal shifting, and reflections. All right. So the shifting happens when we add or subtract. All right. In shifting, we add or subtract a quantity to either f of x or to x. All right. Or x. Now we are going to talk about something a little bit different. It's called vertical stretching and shrinking, and then we'll go on to horizontal stretching and shrinking. All right. So in shifting, we were adding or subtracting a quantity either to f of x or to x, and then we were evaluating the function after adding a quantity to x, adding or subtracting, as the case may be. So now we'll talk about shifting, and shifting now we'll talk about stretching and shrinking, and that involves multiplication. All right, multiplication and division, really. Okay, so let's read what this says. It says, let f be a function and a positive real number. If a is greater than 1, the graph of y equals, I'm trying to get my pointer out. If a is greater than 1, the graph of y equals a multiplied by f of x, a times f of x, is the graph of y equals f of x vertically stretched by multiplying each of its y coordinates by a. So let me just explain that a little bit here. So in vertical stretching, what happens is we multiply, okay, it involves multiplying f of x by a quantity. However, that quantity, whatever we are multiplying it by, has to be a value, okay, it has to be a value greater than 1. So let's say that multiplicative value is a, if that we are using the variable a to represent the multiplicative value. If a is greater than 1, then it is stretching. Then the graph gets stretched vertically. So so think about vertical stretching as holding a rubber band and pulling it up. All right, you have a rubber band and you pull it up. That makes the rubber band tall and narrow, right? On the other hand, shrinking, and we'll go through an example of this. On the other hand, shrinking happens when that multiplicative value is a quantity, it's a quantity between 0 and 1. All right, so that means they are fractional values. All right, like 1/2 is a value between 0 and 1, or 1/3 or 2/3. All right, so any value which is less than 1, all right, but greater than 0, that means a positive fraction less than 1. When that's what the quantity is, it's a fraction value between 0 and 1, then the graph gets vertically shrunk. All right, so let me write that here. In shrinking, what happens is a is a value between 0 and 1. All right, then the graph gets, it shrinks. It's when you stretch a rubber band, it becomes tall and narrow, right? When it's shrunk, all right, when you're not stretching it, it becomes flatter, right? The rubber band becomes flatter and broader. Okay, so that's what vertical stretching and shrinking are about. Just keep in mind that in stretching and shrinking, you are multiplying f of x by a quantity, which we often represent with the letter a, and it's stretching if a is a value greater than 1, if a is a value between 0 and 1, less than 1 but greater than 0, which makes it a fractional value, then it's shrinking of the graph. So we'll go through an example, and maybe that would help us understand it a little. Right, here's an example of the vertical stretching of a graph. All right, so they've used the absolute value function here. The base function is f of x equals the absolute value of x, but they want us to draw the graph of g of x, which is the transformed version of the base absolute value function. So 2 times absolute value of x is the transformed function, right? So this represents our a, the number 2, with which we are multiplying um, the absolute value of the x. That represents a. So the form is, for vertical stretching, the form is hold on one second, it's y equals, all right, a times f of x. All right, so in this example, a is 2, all right, and 2 is a value greater than 1, right? So just recall what we studied in the slide before. If a is greater than 1, then the graph gets stretched vertically. Graph is stretched. And by stretching, we mean that it becomes a narrow graph. All right. So let's see what they've done. The blue graph is the graph of the basic absolute value function. When we multiply the absolute value function by 2, so every y value gets multiplied by 2, the result is this red V, the red graph. And as you will note that this graph, the red graph, is much narrower than the blue graph. All right, so think about it like this. The blue graph has values of x. So when x is 2, all right, when I'm just looking at the blue graph, all right, so just focus on the blue one. When x is 2, all right, y is 2. When x is 4, y is 4, right? When x is 6, y will be 6. And same thing for the negative values of x, we will have the same positive value, all right, the absolute value of the negative values. But in the transformed graph, each of the values, all right, x values, get multiplied by 2, so they double. So in other words, when x is 2, y is 2 times 2, 4. So you see this point here, this is x equals 2. In the transformed graph, the y value is at 4, 2 times to be multiplied the original absolute value function by 2. All right, same thing here. When it's 4, when x is 4, the y value is 8. All right, where's 8? Somewhere here, right? So that's why the red graph, the transformed graph, is rising faster than the original function. Why? Because we are multiplying each of the y values by a quantity which is greater than 1. All right, so the result is vertical stretching of the original graph. Now we'll talk about the final kind of transformation, which is called horizontal stretching or shrinking of graphs. Now the horizontal stretching happens when we multiply the x value, when we multiply the x value by a quantity. All right, let's say the quantity is represented by the letter C. So the graph is y equals f of C times x. So we first multiply the x value, the domain value, by a certain quantity, and then we evaluate the function and get the value of y. Now if the quantity C that we multiply the x value with, if it is greater than 1, then the graph is horizontally shrunk. It's a horizontal shrinking happens. If the if C is a value between 0 and 1 instead, then the graph is horizontally stretched along the x-axis. So I'm going to quickly explain that with the sine function graph, because it might be easier to visualize the horizontal stretching and shrinking on that. Okay, so quickly, and you don't have to worry about this function because we don't do that in this course. That's something we learn in pre-calc 2, but I'm just using that function to explain the concept of stretching and shrinking. So let's say we have 0, 1, 2, 3, 4, 5, and so on. 6, all right. So what's going to happen is, if we let's say the original function is a function like this, all right. It goes up from 0, and then it peaks at 1, and then it comes down at 2, and then again goes you know hits the bottom at 3 and then goes up to 4. Okay, this represents one cycle of the graph, whatever function it may be. All right, so if this red graph is the original function, whatever it is, let's say f of x. Okay, now if we multiply each of these x values before calculating the y values, if we first multiply each x value by 2, all right, then what is going to happen is, because 2 is a value greater than 1, the graph is going to shrink. The graph is going to shrink. It's going to span a smaller area of the x-axis. All right, so the transformed graph is what was before completing between 0 and 4 is now going to complete between 0 and 2. So the graph is going to look like this. All right, it's going to look like this. So this is what we mean by horizontal shrinking. All right, what was spanning over, if the original function was spanning over this much portion of the x-axis, then if we multiply the x values by 2 in the transformed function, then it's going to span a smaller region of the x-axis, exactly half of what it was doing before. On the other hand, if it's like this, if it's f of half x, which is where half is uh, a value between 0 and 1, then the graph is going to span a much wider portion of the x-axis, and that would be horizontally stretching the graph. So let me do that here. Let's say I'm going to extend this 7 and 8. All right. So the original function was spanning between 0 and 4. If c is 1/2, then it's going to go all the way. It's going to go over 8 units instead of 4. All right. Let me draw it here. Okay, so I'm using the green ink. It's going to look like this. It's going to span a wider section of the x-axis, and that's what horizontal stretching implies. All right, so if the quantity you're multiplying x with is a value between 0 and 1, then it's stretching. So you see this green graph is spanning a wider portion of the x-axis, whereas if it is a value greater than 1, then it spans over a smaller section of the x-axis. All right, so that's what horizontal stretching and shrinking means. This is a specific example of horizontal stretching and shrinking. They have used the quadratic function as the base graph. So this blue U-shaped parabola is the graph of f of x equals x squared, which is the base function. And they want us to graph g of x, which is half x squared. So again, please note that they have multiplied the x value first by a quantity, a certain quantity, and then they have calculated the square of it and found the y value. Now, because the multiplicative value c is number between 0 and 1, 1/2. Therefore, this is going to be a horizontal stretching. So it's going to span a wider area of the x-axis. All right, so this blue graph, as you can see, spans a certain section of the x-axis, but when we multiply the x coordinates with 1/2, it spans over a wider area of the x-axis. All right. Okay, now we are going to talk about an example which combines all the different transformations that we've learned so far into a single function and produce the graph of that. All right, so it's a combination of all the different functions or all the different transformations that we have learned so far, which is vertical shifting, that's moving up or down, horizontal shifting, moving left or right. Then we talked about reflections, that is the mirror image of the graph. And then we talked about vertical stretching and shrinking. and then finally a horizontal stretching and shifting. So let's see how many of those are combined in this function here. All right, so I'm going to write out the forms of the different transformations that we learned. Unfortunately, there's not much space here, so it's going to be a little bit congested. But first, we'll talk about the vertical, okay, the vertical shifting. Okay, so vertical shifting was adding a quantity to the function. All right, so you evaluate the function and then you add a function. And it said if k, all right, this k, just k, is a positive value, if k is a positive value, then you shift up, the graph shifts up by k units. If it is a negative value, if it's a negative value, it moves down. All right. As for the horizontal shift, the form was f of x minus, all right, it was f of x minus h. That's the form. And again, we look at the value of h. If h is positive, the shift was right. If h is negative, shift is to the left by h units. All right, so you have to kind of remember the form in your head. So for vertical shifting, it's f of x plus k. It's f of x plus k. If it is a horizontal shifting, then it's f of x minus h. All right. So let's look at this equation. The basic equation is a quadratic function, right? And the graph of the quadratic function is f of x equals x squared with it's a U-shaped parabola opening up, and it has its vertex as 0, 0. So I'm going to first identify the h and k in values in this form. For the time being, don't worry about the minus half. We will look at those after we figure out the h and k value, after we figure out the shifting. So the form, again, excluding minus half, is, let me open my pen again, it's x plus 1 whole squared minus 2. All right, so over here we have minus 2. This part, all right, represents the vertical shifting. This is our k. However, the form of k here, the generic form, is f of x plus k. So if we pull out the plus from the minus, then k, the value of k is negative 2, isn't it? All right, the value of k is negative 2. So if k is negative, then it shifts down 2 units. Okay, it shifts down 2 units from its original position. So what was the vertex, which was anchored at 0, 0, is going to slide down 2 units. Say this is 1. I'm trying to scale it. This is 1 and this is 2, let's say. All right, so this is where the vertex is going to straight slide down. This whole graph here is straight going to slide down to negative 2. Now let's look at x plus 1. All right, so for x plus 1, the form is x minus h, isn't it? X minus h. So if we pull out the negative from the plus, if we pull out, I'm trying to figure out the value of h, all right? So we have x plus 1 here. The form is x minus h. So I'm going to write x plus 1 in exactly the x minus h form without changing it. So it's going to be x minus, if we pull out a minus from the plus, it'll be negative 1, isn't it? So our h is going to be negative 1. So h equals negative 1. Therefore, once it goes left, moves left, shifts left by 1 unit. So we said the vertex would, by the vertical shifting, the vertex would move down 2 units, but by the horizontal shifting from this point, -2, it would slide down to the left by 1 unit. Okay, it slides left by 1 unit. All right, so that means the vertex is going to be right here. It's going to be here. All right. Now that we have figured the shifting out, let's look at just this portion here, the multiplicative. Don't look at the negative. I'm not going to look at the negative yet. We'll keep that for the end, right? Just look at the half here. This is the multiplicative. So this function is getting multiplied by 1/2, which means it's vertical shrinking. All right, it's vertical shrinking. That means the graph, all right, is going to be a wide graph. It's not going to be a narrow graph. It's going to be wider than the original graph. All right, so with the vertex being here, we all figured out where the vertex would be, but it would be a broader U than the original blue U up there. All right, so I'm going to make it somewhat broader. And excuse my drawing, but this is what the U maybe is. You see, this U should be, let me try to do a better job here. Right, anyway, I'll try to make it a little bit broader. And then, all right, now that we have got the shape, okay, its width and its vertex at the right location, we can look at the negative. All right, it's like negative g of x. So when it's negative g of x, then what happens, it is reflected across the horizontal line. So if the horizontal, let's draw an imaginary horizontal line here. Okay, it's a reflection across the x-axis or the horizontal line. So what is going to happen is this graph, this red graph is going to be it's going to be a downturn graph, in other words. All right, this negative sign in a parabola makes it a downturn graph. All right, so that's the end result of the graph of this transformed function.